Okay, great. Hi, everyone. Welcome to our seminar. So today's seminar will be given by Zhaoran Wang from Northwestern University. Zhaoran get his bachelor from Tsinghua University and the PhD from Princeton University. He has got numerous awards, including AI Stats, ASA, Best Paper Rewards, and Informed, and also get an SF career. So he also have some other awards from Amazon and JP Morgan, etc. So today he, Professor Wang would present his new work on the reinforced learning with optimism and pessimism. So please take the floor.
Okay. Oh, thanks so much for the invitation, and it's my great honor to speak here today. So today I will talk about our past work in 2 or 3 years on the theory of reinforcement learning, and hopefully we can touch a little bit about the deep side with deep neural networks. So basically, I will introduce 2 principles. One is more well-known. It is called optimism, which helps exploration in the online setting. And the other is called pessimism, which is kind of new. It is previously developed in the empirical literature, and we had some theoretical work analyzing whether or not pessimism is the right way to deal with the offline setting. So I'll introduce those specific settings in a moment. So this is based on joint work with my longtime collaborator, Zhaoran, who is now a assistant professor at Yale University, and also Ying Jing from Stanford University, who is she's now a PhD student. So I first talk about the general settings. So basically, there are the offline setting and the online setting. The difference is whether or not you can interact with the environment. So in the online setting, you can collect data by interacting with the environment. So there you want to do exploration. And the offline setting, you only have a fixed data set, and you cannot collect more the data point anymore. So that's why it is kind of more difficult in a way. So in the offline setting, I'll introduce the pessimism principle, and we will implement this principle into the classical algorithm called value iteration. And then we can show that there's a provable guarantee for the offline setting. And in the online setting, we'll do exactly the opposite. So we'll use the optimism principle to guide the exploration, which aims at collecting more diverse data points, which is relevant to the optimal policy. Right, so the big motivation is that we have seen a lot of successes of deep reinforcement learning. So the basic idea is that we are combining the representation learning power of neural networks and the decision-making power of reinforcement learning. And in a way, we hope to get the so-called human-level AI. So we have seen a lot of successful examples like playing games, control robots, interact with people, and also recently design computer systems. But on the other hand, we also see a lot of challenges. So for example, if you look at the AlphaGo paper, it takes really a lot of games to train a successful policy through self-play. And there is also a huge computation load. For example, it takes more than a month, even on a very large computer cluster. So same thing happens for training a StarCraft agent. So a lot of years of self-play and more than 1 month of training. And also there's another example from OpenAI where they are trying to play the Rubik's Cube. So a lot of simulation and a lot of computation is needed. So in summary, you will see that we need a lot of data, first of all. If we don't have enough data, then we don't have a reliable policy. So you have seen the failure cases of Tesla autonomous driver. And also there is a lot of computation needed. So there's a lack of convergence, which is kind of well known in the empirical literature. And as a result, if you don't train for a long time, then the policy is not reliable either. So basically, we cannot allow those issues to happen in a lot of critical applications. For example, if you're trading stocks, right, you don't want to have a policy that loses money. And if you're thinking about dynamic treatment regimes, or if you're testing out a new drug adaptively, for example, the vaccine, then you don't want to undesirable consequences. Same thing happens for autonomous driving, where safety is a primary concern. So our goal is to provide a certain level of sample efficiency, and we call it provable because we can mathematically show that if you only have a certain number of data points and a fixed budget of computation, then you can achieve a certain level of optimality with high probability. So that's the provable guarantee we're talking about. So primarily, we're thinking about sample efficiency, meaning we only want to have a polynomial number of data points. But at the same time, we can prove that the obtained algorithm is also computationally efficient. So we focus on the function approximation setting where we're using deep neural networks. So we will focus more on the offline setting in this talk, and we will see that the online setting is kind of exactly the opposite. So offline setting means we're learning from a fixed data set, and there's no interaction with the environment at all. So it's a one-way street. So you can only exploit instead of explore. So this makes the problem very challenging because the data is already given to you, and sometimes the data does not cover all the state and actions you want to see. And then you have to deal with the uncertainty to avoid the more uncertain regions. So the online setting is kind of less challenging in a way. So you can learn from the interaction with the environment, and you want to collect a good data set. And there is a trade-off between exploration and exploitation, which is more studied in the literature. So there, we want to use the so-called optimism principle to drive the agent to the more uncertain regions to collect better data points. So for the offline setting, the challenge is that we often lack a full coverage of the entire state and action space. For example, if the agent starts from the first state, and let's say pi star is the optimum policy, so this is the trajectory we want to reproduce. Right? So let's say our data set covers, well, in a very ideal case, it covers the trajectory of the optimum policy. But in practice, it is very likely that the data set would miss out some of the suboptimal trajectories, which is generated by the policy called pitude. So in this setting, supposedly, there should not be any issue information theoretically because the data set already contains the information needed for getting at the optimum policy. But in reality, if you use the most common algorithm called value iteration, you will see that missing out the suboptimal trajectory, which should not matter, would actually cause a huge issue in that the value function would have some uncertainty along the direction of this trajectory. And then if you just optimize your action given this value function, then the policy would be misled into some other regions, which is probably more uncertain and less safe. So in this setting, we're given a data set, and we have to deal with the data set we have. So we have to know what we do not know about the optimal trajectory, and we want to quantify the uncertainty. So those two challenges together makes the problem very challenging. So first of all, we want to quantify the uncertainty, but the data set is arbitrarily collected. And on the other hand, we want to use this uncertainty to deal with the issue of insufficient coverage. So we want to exploit this data set to the maximum degree. So when we have function approximators, this problem is more complicated. So in the online setting, on the other hand, we want to deal with the problem of exploration versus exploitation. So in the offline setting, we only have exploitation. So in online setting, we want to balance, for example, whether or not this little robot wants to go to the new place, which is more uncertain, or the usual place, which it knows is very good. So in the RL setting compared with the Bandit setting, we have the so-called deep exploration problem, where we want to look into the future and propagate the uncertainty in the future to the current step. And then we use that uncertainty to drive the exploration, which adaptively acquires the data. So then the associated problem is that how do you drive this exploration process using some incentive, which is associated with the uncertainty. And when we have function approximators, this also becomes very challenging because for function approximation setting, we want to deal with continuous state and actions. So just an overview of our results. So when we have the offline setting, we can develop an algorithm based on the so-called pessimism principle. So it's a first provably sample efficient offline RL algorithm without any assumption on the data coverage. And as a byproduct, it turns out our algorithm is also computationally efficient. So we have 3 examples with linear function approximation, kernel function approximation, and neural networks. So the algorithm is based on uncertainty quantification, and we just get the confidence interval, and then we incorporated it into the least squares value iteration algorithm, which deals with continuous state and actions, continuous states. So for now, we can assume discrete actions for the moment, although it is extendable. And then we can use the lower confidence bound, which is illustrated here. So we have a true value function, and we're trying to find a lower bound of the true value function. And then we'll make decisions based on this red curve. And then we call this a pessimistic version of the value function. And in this way, we will get a polynomial sample complexity. So the arrow scales with 1/√t, where t is the number of trajectories, and h is the horizon. So it's also polynomial dependency. And delta of f is the complexity of the function class we're looking at. So in this way, we're taking the lower confidence bound, which can also be viewed as a penalty function. So by incorporating this penalty, we can ensure the epistemic robustness. So epistemic uncertainty means the uncertainty associated with the lack of observation. So, so we can be robust against this type of uncertainty. And at the same time, we can show it is polynomial in runtime, and it is minimax in the linear setting. And in a way, we can show that this is the best we can do in the worst case sense. There's no algorithm that can do better in the linear case. Okay, so that's the offline setting. And in the online setting, we're dealing with something that's kind of the opposite of pessimism. So it's called optimism, which is more studied. But our contribution is that we can give an algorithm that is sample efficient and computationally efficient when there is function approximators. And we can deal with the 3 kind of function approximators. And the algorithm is almost the same. So the only difference is that now we're taking the upper confidence bound. And equivalently, we can show this is also a type of bonus function added to the value function. So we're using this bonus function as an incentive to drive the exploration process. And we have a polynomial dependency on the horizon as well, and dependency on the function class complexity, and also sqrt regress. So this is optimal dependency as well. So also we can get a polynomial runtime. And in particular, when we do this kind of exploration using a bonus, we can show that you don't need any sampling assumptions. You don't need any assumption on the data itself, because you're collecting the data set from the scratch. So just by using this kind of optimistic exploration, you can collect the data points that is helpful for learning the optimal value function. All right, so that's the overview. And also I want to briefly introduce what we can do based on those basic algorithms. So what we'll talk about is basically the regret part and the sample complexity part, which is kind of the foundation. And also we can deal with neural networks using the trick of overparameterization. And on top of them, we can think about more advanced issues like safety, risk, and adversarial robustness. And even on top of that, we can think about the scalability across different agents and the fairness of division, for example, of the reward, and also how to incentivize the agent to do something we want them to do. So there are quite a few extensions on top of them, and you can find them on my webpage. So those are some more recent papers. So I'll pause a bit for questions.
Sorry, just quickly, the word optimism and pessimism, why did you choose it this way? Why not switched?
Oh, so optimism is kind of, we are chasing the uncertainty, right? The more uncertainty, the better. The pessimism is that we want to avoid uncertainty. So we penalize the regions with more uncertainty. So optimism means that, like, I want to explore the places where I have not visited before. So this is kind of an optimistic altitude towards life, right? And pessimistic means if I have never been to this restaurant and I've never seen a data point in my data set about this restaurant, then I certainly do not want to go there, right? Because I do not have the ability to collect more data points, and then I have to make my decision right here, right now. Right? Then I want to avoid those more uncertain regions. That's why it's called pessimistic, or you can say I'm more conservative. Right? Other questions? All right, then we can go on. So I'll first briefly introduce the background of MDPs. So we have an agent, and the agent can take an action based on the policy pi. And this is our policy of interest, and we want to optimize this policy. And then taking this policy will interact with the environment and have two consequences. One is that you will receive a reward following a reward function R, and also you will receive the next state following a transition kernel. And we call it reinforcement learning because those two elements are unknown, and you need to learn those two things. And usually in the literature, for simplicity, people assume the reward is known because the transition kernel is kind of the major challenge. And the challenging setting is that the state is the state space is infinite, and the action space for now we assume it is finite, although the extension is straightforward. And we're considering a finite horizon setting, which means the interaction will end after capital H steps. So you go from the first state, take an action, receive the reward, and then you transit into the next state. And this is determined by the environment. And in total, there are capital H steps. And we care about the expected total reward, which is J of pi. So we want to maximize this pi, let's maximize this total reward over pi. What we have is the trajectory of pi. So it contains state, action, reward. This expected total reward over the H steps is our optimization objective. And we want to get to the argmax of J of pi, which is the optimal policy. So that's the basic setting. Usually the way of designing the algorithm is that we can look at the so-called dynamic programming principle. So at each step, we want to do our best with respect to the future reward in expectation. So here, Q star function means that if you take the optimal policy at the current state and action, and as long as you take the greedy action with respect to the optimal Q function, then you can make sure that this policy from this point on is optimal. And then you can do this in a backward manner. And it means that at each step, you're doing your best. So this is just a recursion across all those H steps, and it is going backward from the last step to the first step. And we call this operator the Bellman operator. So here it involves both the reward function R, which usually needs to be learned, but for now we can assume it is known because the transition kernel is more challenging. And here the transition kernel appears here. So you're taking an expectation with respect to the next state. So it means that if I'm doing my best from now on, and then if I'm also doing my best for the current time step, for example, for today, then I can ensure that I'm doing my best throughout my life. Right? So this operator, which involves a max, is called the Bellman optimality operator, which we will write as capital B. And doing this recursion gives us a very simple equation called the Bellman equation. So we can go from the last step to the first step. And at each time, we just apply this Bellman operator, although we need to learn this expectation and in some other cases, the reward as well. So it contains unknown quantities, which can be learned from the data. So in reinforcement learning, we usually have continuous state space, for example, images and, when you trade stocks at the prices, right? So we have to use a function approximator, which maps from the state and action to a scalar, so to approximate the Q function, and in particular, the optimal Q function. So we can also use neural networks as well. So it will be covered late in the talk. So in the offline setting, as I mentioned, we will talk about the pessimistic value iteration algorithm, which incorporates a penalty to avoid the more uncertain regions. So again, just to recall, the protocol here is that we are learning from a given data set. A given means that you cannot collect more data points from the environment. So it's quite challenging because it's already given, and what's not known is already there, right? So you want to avoid those more uncertain regions using pessimism. And we'll see that even in the simplest case of multi-arm bandit, not knowing, not observing a certain arm would cause a huge issue. So we have an agent, and then it can only deploy the obtain policy to the environment, but this is one shot. What you really have is the data set collected from the environment. So it means T trajectories, and it is collected a priori, so it's just given. And then we want to find an algorithm that can find a pi hat. That's a policy we want to get. So the strategy we usually use is that we can estimate the optimal Q function, and this algorithm outputs the optimal Q function, and then we take the greedy action with respect to this Q hat, the estimator for the optimal Q function. So basically, it's just a two-step algorithm, right? So as we all see, it consists of two steps. One is estimation from data, and then you optimize your action based on this Q function. So again, there's no further interaction with the MDP, and we care about maximizing the expected total reward, J. And we have the benchmark of the optimal policy, and later we introduce other benchmarks as well. For example, the best policy covered by the data set. And then we have the pi hat, which is the policy obtained from the algorithm. So here's the most commonly used algorithm, and it's covered in a lot of textbooks. So it's called the value iteration, and for continuous state and actions, for continuous states, for now, we assume action is discrete. So we are using the least squares procedure. So in total, we have 8 steps. So we're going backward using the dynamic programming principle. So the initial condition is that the value function is 0 for the last step because there's no reward to collect when you go to h+1. So that's the boundary condition, as we mentioned. So then you do the backward induction. So every step, you use the data points to perform a regression. And then you want to estimate the Q star function, the optimal Q function. So here, the regression function, which is a conditional expectation, is the Bellman operator applied to the previous Q function. Okay, so Bellman operator is unknown quantity, which needs to be learned from the data because it contains reward and transition kernel, which are unknown. And the two elements you have, one is the data set given to you, and the other is the function class we can use. For example, linear functions or neural networks, and so on. So if you write down this regression problem, we can explicitly write down the y and x, which is y is the reward plus the max of the previous Q function, and the x is just the current state and actions. Okay, so that's clear. And the thing we have is that, again, the data set, function class, and this is unknown. So regression function B applied to Q hat is unknown. So then after obtaining this optimal Q function, things become very easy. You just optimize the action, right? Taking the greedy action is the best because of the Bellman equation. And then doing this recursively, we can get the optimal policy, hopefully. So then the question is, when does it work, right? So what kind of assumptions we need and whether or not they can be satisfied in practice. The first one is that the function class is very rich in the sense that it captures the image of the Bellman operator. The other is that the data set covers the entire state and action space. So note that this is very strong assumption, right? So in practice, you never test out all the possibilities. For example, if you're testing a drug, you never try those drugs that are less promising. So this shouldn't be an issue. But in reality, if you use this algorithm, it really becomes an issue because of the uncertainty. Okay. So, so this assumption is usually ensured by For example, assuming there's a generative model which generates the reward and next state for any state and action that is given to you. So in reality, this is quite challenging because if you're playing the Atari game, you cannot jump to any state and action as you want. You really have to play the game from the scratch, right? Starting from the initial state, and then you have to be very strategic about reaching a certain state and action. Right? So there are other sampling assumptions, which is usually known as concentrability coefficient, which is kind of used in a lot of the literatures, including our own paper. So, and then we want to eliminate this kind of strong assumptions, primarily the second one. The first one is kind of necessary because you want the function class to be rich enough, otherwise you would have a bias, although the analysis can also deal with this kind of bias. So the second assumption is quite restrictive and is violated in practice, and we'll see why and how it fails. So first, for example, let's think about the typical setting, right? So this is quite a nice setting because the data set already covers the optimal trajectory, but it kind of misses out the suboptimal trajectories. Supposedly, this should not matter because this pi2 does not contain any useful information for learning the optimal policy anyways. So it's not relevant. So you will see that this particular algorithm, the classical version, will fail even in a simple Bandit case due to this kind of uncertainty. So let's think of a Gaussian Bandit. You have the mean reward. For example, the first arm is optimal. The mean reward is 3. The other reward are 0. Okay, those are all suboptimal arms. I want to select the best arm, which is the first one. And let's say I've visited the first arm for 10 times. Let's think about the drug testing setting, right? So because the first arm is quite promising, then I have tested it for 10 times. I collected 10 observations, and then that gives me a better estimate for the reward. So for the other arms, I have only visited them for 1 time because they are less promising, and we know, well, I just tested once, and probably I can just eliminate this arm. So in this case, because we don't have any state, so Q function just boils down to the reward, and estimator for the reward is just the sample mean. So it's an unbiased estimator. The mean is 3, and the variance is 0.1 because we have visited it for 10 times. And for the other arms, we have visited for 1 time. So variance is much larger. The mean is also 0. So supposedly, we should be selecting the first arm. But in reality, because of this very high uncertainty, so much larger variance, if you have 1,000 arms that are suboptimal, so it is very likely that just by chance, one of the suboptimal arms happens to have very high empirical mean, then you will be selecting the suboptimal arm, which is not the optimal one, which is the first arm. Okay, so in this case, you suffer from the suboptimality of 3, and you're picking the wrong drug. Right? And a simple fix to this problem is that you can just penalize this uncertainty, and we call it epistemic because it comes from the fact that we do not have a lot of observation about this particular arm. So this comes from the uncertainty of the estimator due to the lack of observation. Okay. So if we take the lower confidence bound, which is the sample mean minus the width of the confidence interval, right, or the variance of the estimator taken square root, then you will see in this case, it will be very safe, right? Because I have visited the first arm for 10 times, then I'm just subtracting a very small quantity. But for the other arms, I'm subtracting a very wide confidence interval. So it takes a huge penalty for them. Then you will be selecting the best arm. Okay. So in this case, you will see that even if my data set misses out a lot of the suboptimal arms, it is still fine. I'm taking the optimal arm. Okay, I'll pause a bit for questions.
Yeah, so Zhaoran, for those suboptimal arm, you only have 1 data. How can you estimate their variance to?
Oh, yeah. So in this case, so this variance is not estimating in practice. I'm just saying that the mean estimator has the variance of 1.
Okay.
Yeah. But in a moment, we'll see that in this case, it is easy to construct a confidence interval. Right? So that's in this case, it's just 1 over square root of number of visits to this arm.
Okay.
Yeah.
Good.
So so the algorithm, given this idea, is almost the same as the classical algorithm, but we just add 1 extra step, well, 2 extra steps. So previously we said we want to do estimation and then make the decision by optimizing the action. So now we have 2 extra steps. Okay, so the original steps are in blue, so the estimation and optimization steps. So the thing we add are those 2 steps. One is quantifying the uncertainty. For example, we can use 1 over square root number of visits to the arm, and we can construct a confidence interval, or construct like calculate the width of the confidence interval, and then we can subtract the width of the confidence interval as the penalty to the original Q function. So in the multi-arm bandit case, this is just the sample mean estimator, and this is the 1 over square root number of visits. And this we call the pessimistic version of the value function. Okay, so this is the lower confidence bound. And then we simply do the old trick again, right? We just take the greedy action and return the path. So that's the twist. And for the next iteration, we'll just use the Q minus the pessimistic version as the Q function, and then do this again until we reach the first step. So we call this pessimistic because mathematically, you always have a lower bound of the optimal Q function. So, and this confidence interval ensures that this range contains the, the ground truth, which is regression function. It's the Bellman operator applied to the previous Q function with high probability. And it is useful to remark that here we are considering element-wise confidence intervals. So in the follow-up works, there are a lot of other ways to think about this. So you can construct the confidence interval like over distribution in an L2 sense instead of L infinity sense. So that's also possible. And there are other ways to construct confidence intervals as well. And potentially, those confidence intervals are even tighter for the purpose of minimizing the error or maximizing the expected total reward. Okay, so but the idea is the same. So the theory says that, well, if I'm trying to compare against my optimal policy pi star, and pi hat is the policy we get from the algorithm. So you can get a guarantee that only relies on the trajectory of the optimal policy. So gamma, again, is the width of the confidence interval. So it means like how many times you have visited the state and action. Although in the continuous case, we have to be more careful about what it means to say the number of visits, right? Because for continuous state and action, you almost never visit the same state again. So there are other ways of constructing this gamma. And I'm summing up the width of the confidence interval across all the H steps. So the major point is that here the state and action follows the optimal policy. So we don't have to care about how many times we have visited a suboptimal trajectory or suboptimal state and action. So in the bandit setting, you will see this immediately translates to the number of visits to the optimal arm. So in our previous example, it's 10 times. So it scales as 1 over square root 10 in that case. And we don't have to care about the suboptimal arms, which is only visited for 1 time. Okay, so this arrow is significantly smaller. By using this trick, first of all, we formalize a lot of useful heuristics in practice. And also, we'll see that you don't need any coverage to make this work. So this thing only requires that the data set visits the optimal trajectory for a sufficient number of times. Also, another remark is that you can just modify this pi star to be any benchmark you want. So the guarantee will be the same, which means that you can enumerate over all the policies that is sufficiently covered by the data set. And then you can hope to compete against this policy with a certain type of optimality guarantee. Okay. So for example, if your data covers a suboptimal trajectories, but that's my goal. I just want to compete with the suboptimal trajectory, then you can get the same guarantee. And the proof is the same. Okay. And we only require that the Bellman operator to map a function into my function class. So that's kind of a requirement. Otherwise, you have a bias. To translate into the statistical guarantees, we can show that if you data set covers the optimal trajectory for t times, and we don't need the full coverage of the entire state and action, then we get a 1W-T rate, which is kind of the optimal rate we usually see for the error bounds. And the only requirement for the linear case is that the covariance matrix is positive definite. And here, by the pessimistic trick, we can take the dependency into the dependency on the pi star, the optimal policy. Okay, so, and also at the same time, we can show that this type of requirement is optimal for the linear setting, because so basically it shows that there's nothing that can do better. So although our dependency on the D is not optimal, but we first of all, we care about the 1W-T dependency currently. So that's the offline setting. I'll pause a bit for questions. All right. So then we can think about the online setting, which is kind of, you know, the dual to the offline setting, right? So here we're using the opposite trick. We're taking the optimistic version. So everything will be the same except the sign. All right. So the interaction protocol is as follows. So here we are learning by doing. So we are trying to interact with the environment. And then the question is, where do we want to do the exploration, right? We want to collect more data points, but which data point we want to collect? So here's an agent, but in the online setting, it tries to interact with the environment by taking a policy. And then it will generate state and actions, which is given as a trajectory. And then we have a bigger data set. We just have the previous data set with the trajectory. And then we just learn the policy again. For example, we can think about offline our algorithm. And given the data set, we can usually get a new policy, no matter what kind of algorithm you use. And then we deploy the policy again to collect more data points. In total, we can have T rounds of interactions. And within each round, there are H steps, okay, for the finite horizon setting. So here we care about the comparison against the benchmark, the pi star, the optimal policy. Excuse me. And we want to minimize the regret, which is the sum of the suboptimality, of course, the T rounds of interaction, T episodes. And if you spell out the regret, then you can get a more concrete definition. So you just collect all the reward across the T steps and H steps. So this should be capital H. And then we have a total number, the total amount of rewards collected by the optimal policy. So that's the gap. And hopefully when we're collecting more data points, we can minimize this regret, and it should scale as something sublinear in capital T. And here we face the dilemma of exploration of versus exploitation. So again, the algorithm, as a value-based algorithm, it decomposes into two steps. One is the estimation of the optimal Q function, and the other is the optimization of the action. So you want to take the greedy action once you get the Q hat. Okay. So if the Q hat is just the optimal Q function, then you will get the optimal policy. So again, the assumptions are, first of all, I hope the function class is rich enough to capture the image of the Bellman operator. And second, I hope the data set can cover all the state and actions. But this is indeed kind of impossible in practice, because you're collecting the data set from the scratch and you're adding one trajectory to the data set each step. So at the beginning, you cannot hope this is true. And then the question is, how do I find this data set? What kind of trajectories do I want to collect to incorporate it into my data set? So a typical situation from the start is like this, right? So you have a policy pi k for the k step, and you observe the trajectory, but you never see the optimal trajectory. So you want to move your data set towards the left by doing exploration. So for example, this little robot wants to go to the new place every now and then just to test out whether or not it's good, right? So we have to take some risk of exploration, just to see new things. So then we have to balance exploitation versus exploration, because you don't want to suffer from a huge regret if this new place is not good, right? So so this becomes very tricky, especially in the reinforcement learning setting. So in Bandit setting, you already have this concern, and in the reinforcement learning setting, this concern is more outstanding. So if you have multiple steps, and then if your reward is received as the last step, and then it's a bit challenging, because if you have to stick with the good option every step to reach the high reward. But if you do random exploration, like you just select a random action at each step, then it is very likely you will arrive at a bad state that gives you a small amount of reward per step, but eventually it leads to nothing. Okay, you have to stick with the good options, good actions at each step. So in this case, you will see that if you have a lot of suboptimal actions, if you do random exploration, then the probability of reaching this high reward is exponentially small. So that's why we have the so-called deep exploration problem. So you really have to look into the future to get the good action. And in this case, our goal is to achieve the sample efficiency, which means a polynomial dependency on the horizon, and the sqrt dependency on the number of episodes we collect. So here you will see, in this case, doing random exploration is not enough. You really have to backpropagate this uncertainty for the last step to the first step to make a good decision, so that the first action will influence the exploration as the last step. Okay? You have to act very early to collect the high reward. So in the literature, the usual assumption is that, well, we want to have a generative model. Given any state and action, it produces the reward and next state, but you can arbitrarily select this as you want. And in practice, you really have to do from the scratch, and that becomes more challenging. So previously, there's a lot of paper studying the exploration problem, especially using the optimism principle. So there are multi-arm bandits, which is very classical, and also contextual bandits, which becomes slightly more challenging because the state space is continuous. And then we have another dimension of extension. We can think about finite state MDPs. The horizon is larger than 1, and the state space is finite. And then we have MDPs with continuous state and actions. So there we have to deal with function approximation settings. So what we did is the linear function approximation and kernel and neural networks. And also there are other extensions to policy optimization, Markov gains, and constraint MDP. So we didn't include all the works of other people. So there are a lot of recent works in this field. So the algorithm is almost the same, except that we are now adding the uncertainty instead of subtracting the uncertainty. So with the two actual steps, we can first estimate and then optimize. But now we're using the optimistic version of the value function. So for the linear, you can construct the bonus function easily by thinking about the confidence interval of the linear regression problem. And here we are thinking about finite element-wise or infinity norm confidence interval. And then we can show that for all state and actions, the Q function is larger than the optimal one. So that means it's an optimistic version. So that's why we use the word optimism. So the guarantee is that now we have a dependency on the function class, which you can think about as the rank of the transition kernel, and also log covering number of the value function class. Okay, so those are kind of the same quantity, for linear classes, but we definitely have the two dependencies. So they are fundamentally different for the exploration setting. And then we have polynomial dependency on the horizon and a sqrt regret, which is the thing we want to achieve. For linear setting, one is d, the dimension of the feature, the other is d squared. So the linear setting, we have this specific instantiation of the general bound. And for neural networks, we can also spell out what is d and what is covering number, log covering number. So here, in general, we only require the assumption that the image of the Bellman operator is contained by my function class. So the important side is that we don't need sampling assumptions. Again, so that's the data side we want to achieve. And at the same time, we can show that this algorithm can be implemented in a computationally efficient manner. So I'm probably running out of time. So just a few extensions. The one is policy optimization. So instead of taking the greedy action, you can gradually improve your policy based on the previous policy. So this pi-old is from the previous iteration. So still estimation and optimization, but now I'm doing the optimization in another way, which is more like mirror descent instead of greedy. So this brings a lot of actual benefits. For example, you can deal with adversarial reward functions, which changes across each episode. But the general principle is the same. We can use optimism. So now we call it actor critic because for the regression, you can think about a critic that evaluates how well this policy is. For the actor, it kind of improves upon the previous policy. So think about teacher and student, right? Teacher provides feedback, and student does the improvement. And also we can handle the gains, which is kind of the min-max setting. Right? So here, optimism, pessimism becomes a bit tricky because we have to distinguish like which direction is optimism. Like optimism for you is kind of pessimism for your opponent. And then if you have those confidence intervals, then the subgame you're trying to solve becomes a general sum game. So then you have to be careful about whether or not you want to find the Nash equilibrium, which is very hard computationally. But instead, we show that you can actually try to find the correlated equilibrium, which is easier in terms of computation. And this is also sufficient for getting the Nash equilibrium for the Markov game. So also there are constraint settings where we are concerned about safety. So for example, we want to control the cost to below a certain threshold. For example, we certainly do not want to crash into some other things when you are doing autonomous driving, right? So we have safety guarantees to avoid that during exploration. And we can show that you only need a finite number of violations when you're doing the learning. And in more recent work, there's ways to achieve zero violation. And there they combine the trick of optimism and pessimism, but in a different way. Okay, so those are the possible extensions. Just as a summary, so we're thinking about two regimes. One is the offline setting, and there the problem is that we don't have sufficient coverage of all state and actions, so it can miss out certain trajectories. In that case, we want to be robust against this kind of uncertainty because the uncertainty is there, is inherent, and there's nothing can be done about this uncertainty. You cannot collect more data points in any ways. And there, pessimism improves the robustness, and we only needed the coverage of a certain benchmark policy. It can be the optimal policy or any other policy you want to compete against. So in the online setting, the situation is kind of the opposite. When you start from the scratch, your data set does not cover the optimal trajectory. Then you want to move your data set towards the left, right, to cover better trajectories to help learning. And at each time, your data set would change. So there we're dealing with the issue of insufficient coverage of the optimal policy. And there we want to do exploration to minimize this uncertainty. And we want to go to the places that are less observed in your data set. So we're using optimism to incentivize exploration. So that's the general picture. Thank you a lot.
Great. Yeah, thanks, Zhaoran, for a great talk. It's